Good morning, students. May 11th, 2 months into our pandemic stay-at-home remote learning order. Everybody's outside with masks on. I hope your family is healthy. I'm getting ready to write down some notes on electric current, and we're going to be starting to talk about electric circuits. And so we're moving forward. Hope you're all well, and let's get started. All right. So I'm going to flip this tablet down. It's going to make a little noise for a minute, and then I will begin to write on it. And you have the option to use this template, or you can just record these notes in your textbook, or you can read the chapter and record your own notes. I kind of distill what's in the chapter down into what I think is important to know. All right. So let's see. Electric current. The idea of current. Where do we think about current originally? Probably when we think about water. Water is a really good analogy for electric current. And so let's think about water for a minute. Imagine you're walking down the street. Here's the street. And you notice a puddle of water. Here's the nice puddle of water. Would you call that current? No, probably not. It's still. It's not moving. This puddle is not moving. Maybe this time of year it is, what do you call that in biology? A vernal pool, water that's not moving. It's just still. That's where frogs and salamanders tend to live. But it's not moving, so we don't call it current. Where would you see current? Where would you see flowing water? I spend a lot of time up on Mount Tom these days. And if I imagine a mountain, then after it rains, the water comes rushing down the mountain, and that would be considered current, right? So here's my my blackboard, whiteboard version of water flowing. And so how do I imagine in physics that this water begins to flow? Well, you know that at the top it's got some potential energy, and the water moves in such a way as to minimize its potential energy. So down here it has a very small amount of potential energy, and up at the top it's got a lot of potential energy. So flow, or I should say water, flows in a manner that minimizes its potential energy. That's true of everything too. I mean, when we initially started talking about potential energy, we were talking about lifting a book up above the surface of the earth, and if we let that book go, it falls to the earth in order to minimize its potential energy. And so that's exactly what water does. So water is the flow, or I should say current is the flow of water from a location of higher potential energy to a location of lower potential energy. All right. And so I wrote that down here. I don't exactly know what this little thing is. I have no idea. Oh, and there it went away. So water flows from regions of high potential energy to regions of low potential energy. If there is no difference in potential energy, there is no flow. So we use that exact same analogy to talk about electric currents, only now we're talking about electrical potential energy. And so what I'm going to do is draw a battery. And you should get into the habit of drawing batteries. So this is like a D cell. A nice big fat D cell battery. Probably it's 1.5 volts. D cell batteries are 1.5 volts. The little nubby thing at the top indicates the positive end of the battery, and the other end of the battery, sometimes it has an indent. That's the negative end of the battery. And so there's a potential energy difference between the two ends of the battery, between this end and this end. And volt means joule per coulomb. We talked about potential in the last chapter. So this is 1.5 joules for every coulomb that flows through that battery. Each coulomb gets an additional 1.5 joules of potential energy. All right. You could think about it as 1.5 joules of PE for each coulomb up here at the top, and at the bottom, they don't have, the coulombs of charge have 0 joules of potential energy. And so the job of the battery is to boost the potential energy of the charge so that charge can do some work. Boost the potential energy of the charge. That's what's happening there. All right. So I'm going to get rid of this green, and I'm going to draw a little electric circuit. And I'll ask you to go ahead and draw that same electric circuit. All right. So our very first attempt at drawing an electric circuit, we start with a battery. Have to have a battery. Then we need a wire coming out of both ends. So for a circuit, I need a complete loop for current to follow. And then I'm going to attach this to a light bulb. And a light bulb has a little filament, and that filament will glow. If there's current flowing, it'll glow. All right. So here's my circuit loop. A circuit is a complete loop. Complete loop with no breaks. A complete loop for current to follow. You should be able to trace it, right? Out of the positive side, through the light bulb, back to the negative side. And then what does the battery do? It boosts the energy of the current of the charges so that they can flow around that loop again. So there actually are little electric charges flowing around that loop, just like the flow of water. All right, electric current. In fact, sometimes you even use a little arrow to show the direction of current. And notice it's coming out of the positive side, going back into the negative side, out of the positive side with lots of potential energy. By the time it gets back here to the negative side, it doesn't have very much. It's used up all its potential energy in the form of heat and light, making that light bright. Heat and light. Okay, so that electrical energy is being transformed. That is the idea behind current. Okay, so a battery provides potential energy to the charges so that current can flow. All right, that's what we've got. So now I'm going to go try to define a few different terms so that we can use them in our electric circuits. We're going to be building circuits over the next couple of weeks. All right. So the first new word we have is current. Current. The symbol for current is I. I don't know why they use an I for current, probably because C is already used for the speed of light. But current indicates the flow of electric charge. And it's actually in coulombs per second. Now think about the flow of water for a minute. If you had a plumber come in to your house and measure the flow of your water out of your shower, he would probably be measuring it in gallons per minute, or maybe liters per minute or liters per second. But you'd have some measure of water up here, and you'd have some measure of time down here. And so we've got something similar. We've got coulombs in the numerator and seconds in the denominator. And a coulomb per second is known as an ampere or an amp. Okay, so the unit that we use to measure current is an amp. An amp, the flow of electric charge. So it's necessary to have a difference in potential energy in order for charge to flow. And so voltage is basically potential energy per unit of charge. Okay, so it is a joule per coulomb. So we were introduced to this idea in the last chapter. Joule per coulomb is known as a volt. A joule per coulomb. So really there is some potential energy that we use to make the circuit work. Potential energy. Could be a battery. It could be the outlet in your house provides 110 or 120 volts of power for you to use. And voltage is symbolized with a big capital V. All right, so that kind of makes sense. Last but not least is resistance. And resistance is anything that you put in the circuit to use the power. So, and why is it called resistance? Because it resists the flow of current. It resists the flow of current. It slows it down. It converts that electrical energy into some other source, whether it's light, whether it's motion, whether it's heat, whether it's sound. And so resistance is, in the analogy of water, it would be like having some hair in your drain that was slowing down the flow of water. In your arteries and your veins, it's kind of like having too much plaque in your arteries, and so your blood doesn't flow very easily. So resistance is any device placed in a circuit which slows the flow of current. Okay, so it could be a light bulb. It could be, I don't know, a heater. It could be a motor. It could also be something called a resistor. Okay, electricians use resistors to actually slow the current down. Sometimes you don't want to have a lot of current flow. You want to minimize it. And so you actually put a resistor in the circuit. So these are things that slow the current. Resistance is measured, well, what is the symbol? It's a big capital R. It's measured in volts per amp. And a volt per amp is known as an ohm. It's exactly the same word that you might use if you meditate. It is the same word, and that is the Greek letter omicron. All right, resistance. So we have these three variables when we talk about current flow. We have I, the flow of current. Current flow is caused by voltage, and it might be slowed down if we have a lot of resistance in our wires or in our circuit. And so Ohm's law tells us how those things are related. Ohm's law says that the current is directly proportional to the voltage and indirectly proportional to the resistance. I is equal to V over R. Okay. And actually that does make sense because volts measures a volt. A volt is the unit for voltage. And we just said that resistance is a volt per amp. And if you do that division, a volt dividing by a fraction is the same thing as multiplying by the reciprocal, amps over volts, and you get out an amp. Okay, and so I is equal to V over R. When voltage is big, that means current is big. If there's a lot of resistance in your circuit, that means the current is small. And so another way to write this is V equals I R. All right, these are both statements of Ohm's law. So if you know the current in your circuit and you know the resistance in your circuit, you can figure out how much voltage is needed. On the other hand, if you know the voltage in your circuit and you know the resistance in your circuit, you can figure out the current in your circuit. And that's what we're going to be working on in the next couple of weeks. All right, what about electric shock? So you all know probably that if you stick your fingers in an outlet, you're going to get a shock. And that shock is going to be a whole lot worse if you have a wet body or if you just got out of the swimming pool or the bathtub. In fact, you should never, never, never have any kind of electricity around water. Really bad situation. Electric shocks are caused by current through the body. stops the heart. So too much current is very dangerous. So how much current is too much current? 1 amp of current is a lot of current flow. And if you go down to your basement and you look in your circuit box, your circuit breakers are probably rated at 15 amps or 20 amps or maybe 10 amps. That is a ton of current. That is definitely enough to kill a person. Luckily, our body has an awful lot of resistance. But if we have currents on the order of 1 milliamp, that is considered something that's pretty dangerous. Okay, so it could be dangerous to humans. More than 1 milliamp, which by the way is 0.001 amp, more than, is definitely bad. So how do we get around this when we've got these electrical outlets that have 110 volts? Well, our bodies offer a lot of resistance. Okay, they offer on the order of 500,000 ohms of resistance. They resist the flow of current when they're dry. Okay, our bodies have a whole lot of resistance. And so if you just use Ohm's law and you take, I want to know the current. So 110 volts divided by 500,000 ohms, that'll give me the current, right? It's going to be very small, very small. Dry human bodies offer a lot of resistance. You're going to read in your textbook that if your body is wet, the resistance that's offered by your body goes down, 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 down. Maybe it's only 500 ohms if it's wet. And so then you could get a lot of current flowing through your body. It is the current that is very dangerous for human bodies. So be really careful when you have electricity around the bathroom. That's why we have those ground fault circuit interrupters. Okay, what about AC versus DC? So AC and DC current. So DC is the easier one. DC current comes from batteries and it means direct current. That just means it doesn't change direction. So here's a little miniature version of my circuit. My little light bulb here. And if I draw the current, it always goes out of the positive end around the circuit, sort of clockwise, and back into the negative end. It always goes clockwise in one direction. Direct current. Alternating current does something different. Alternating current doesn't act that way. So AC means alternating current, and power that's generated by the power plant is alternating current. Alternating current. Okay, so what does that look like? Okay, so here's your electrical outlet in your house. Usually there are 2 in every outlet. And let's say you want to run that same light bulb. So you come out of one side, there's the light bulb, boop, the wires in your house go back to the other side. Kind of acts like a battery, only it's got 110 volts instead of 1.5 volts. Well, here the current goes in one direction. Oops. Current goes this way, and then it goes back again. So it goes forward and back and forward and back and forward and back. It doesn't make a complete loop. It just keeps moving forward and back. In fact, it changes direction 60 times every second, 60 cycles per second. Wow. So it's really alternating back and forth and back and forth and back and forth. It's still going to make that light bulb glow, but it's current that's just not moving in one direction. And that's because of the way it's generated at the power plant. We may have a chance to get that far in our curriculum this year. And we'll talk about that. And we may not. And you can also look it up. Look up power generation. It's pretty interesting how that happens. All right. Last but not least, power. What is power? If you remember back in the unit where we talked about power measured in watts. And I know that if you look at a light bulb, it's rated in a watt. It's not rated in volts or amps, it's rated in watts. So what does watt have to do with power generation? What does a watt have to do with electricity? All right. And so, well, power tells us the rate at which energy is used. Or you could say energy is converted to another form. So if you're using electricity, the electrical power is being converted to light, or converted to heat, or converted to motion, or converted to sound. The rate, okay, joules per second. And so remember, a watt is really a joule per second. Okay, so we have some new variables talking about electricity. How can we put these together to get a joule per second? So, oops, that's not good. So we have this current that measures in coulombs per second. And then we have this voltage that measures in joules per coulomb. So coulombs per second and joules per coulomb. What happens if you multiply those two things together? What if you multiply voltage and current together? Well, if you do that, if I take a volt and I multiply it by how much current flows, I end up getting, so this is a joule per coulomb, and this is a coulomb per second. I end up getting a joule per second, which is a watt. And so power in a circuit has to do with how much current flows and also how much voltage is provided. So if you provide a lot of voltage and you get a lot of current flow, that means you're using a lot of power, all right? And so power in a circuit is the product of the voltage times the current. And so we're going to be using that formula as we think about setting up some electric circuits. All right. So we're just going to start this week by reading chapter 35, answering the yellow box questions. I'm going to ask you to submit those to me this week. Submit a picture of those yellow box questions. And we're going to start looking at chapter 35 worksheet and thinking about how current works in a circuit. Next week, we're going to learn how to draw schematic diagrams, and we're going to do a PhET lab. All right. So I hope you have a good week. I miss you all. Take good care of yourselves and your family. Hope you said happy Mother's Day to your mom yesterday. And I'll talk to you soon. Bye.